It's a great pleasure to welcome you to the Picture Language Seminar. Today, we have Zhengwei Liu. He's been visiting for a few days from Tsinghua University. We miss him here at Harvard because he was here for 4 years as postdoctoral fellow. But we're happy that he's back and maybe he'll come to visit again. He's been doing very interesting work on topological quantum field theory connected to theories in higher dimension and also lattice models in 3 and 4 dimensions. And today he'll talk about insights on analysis meeting topology in quantum field theory. We're very much looking forward to your talk.
Thank you, Arthur. And it's a great pleasure to be back and present my recent work on topological quantum field theory. And I think it's even more exciting since I found this work is related to Arthur's early work in constructive quantum field theory, even though we are talking about the topological version, but they really share a lot of insights between analysis and topology in quantum field theory. In this talk, we will see how this kind of 2 different approach really emerge together in a very natural way. The first, the aim is to understand the topological quantum field theory in all dimensions. And this has been well studied in lower dimensions, like 2+1 theory and 3+1 theory. But when we first found the 2+1 case, and then we realized the method essentially works in all dimensions. But there are some additional mathematical, really delicate topology in high dimensions that we have to be very careful. But on the physics side, it turns out to be very conceptual to generalize the concepts in higher dimensions. So here we propose a program to address this problem with how to construct a meaningful topological quantum field theory in arbitrary dimension. And in particular, for the interest of in physics, we expect this condition, the unitary condition. And in this talk, I will show how to construct such kind of TQFT from a linear functional, which can be considered as a functional integral in the usual sense in quantum field theory. And this is a linear functional on n-dimensional lattice model. And eventually we get to an n+1 dimensional TQFT. And this one extra dimension could be considered as the dimension for a derivative. And the configuration space of the lattice model here, we describe this mathematically as labeled regular stratified piecewise linear n-manifold. There are many very delicate mathematical conditions to really make it work rigorously. But in this talk, I will skip all those kind of conditions. Instead, I will explain the major ideas, in particular, the major physical concepts behind this work.
Here, n is a spatial dimension.
Yeah,
n+1 TQFT and
yeah, actually, if we take the n-dimensional model and then after quantization, n becomes space-time dimension.
Oh, n is a space-time dimension.
And indeed, there is one extra dimension beyond that theory.
So maybe that's so when you do n-dimensional lattice models, you will construct TQFT in n+1 dimension or n dimension. I mean, here the dimension is a space-time dimension.
Yes, if we consider n-dimensional lattice model, then we will get an n+1 dimensional TQFT.
Okay.
The reason is on this n-dimensional lattice model, there is a hidden Hamiltonian acting on that.
Okay.
And that's the one actual dimension. So
So
basically,
n is a space dimension.
it's space dimension, but it's the quantum lattice model.
Yeah.
The quantum description. So I will emphasize that there is really very interesting analytic insights in addition to the previous topological and categorical approach to topological quantum field theory. And topological quantum field theory has been a very rich topic and initiated in the early work of Witten. And he constructed the topological quantum field theory in 2+1 and 3+1 dimensions. And for 2+1, he used the Chen-Simon theory and obtained an inverse of links in 3 manifolds using a path integral. And this generalized the link inverse of Jones polynomial from operator algebra subfact theory, and other linking inverse from the representations of quantum groups of Junfei-Jingbo type. And in this work, the path integral is very powerful. But the measure of the path space is only mathematically defined for a very rare case, such as the development in the constructed quantum field theory in early work of Gleeman and Jeffy. And in this approach, just how to make the passive integral rigorously defined is still not very clear. And but once we know is that if this is a reasonable passive integral, then it should have a crucial condition that's reflecting positivity. And this condition has been used to implement the weak rotation from the Euclidean field theory to relativistic field theory, as shown by Oswald and Schrader. So this is the condition we will take as the analytic part. And to deal with this theory, mathematically, here I propose that this topological quantum field theory is a kind of combination of quantum physics and topology. And this kind of phenomenon emerging from the continuum limit. And this is mathematically defined as a symmetrical monoid functor from the category of cobordisms to the category of vector spaces. And in particular, we can understand this in the n+1 theory. The n manifolds on the boundary as an object, and it corresponds to a vector space. And the n+1 cobordism as a morphism corresponds to linear transformation. And the TQFT is unitary if the partition function is reflecting positive. In this case, the vector space becomes Hilbert spaces. And in topological quantum field theory, most interesting example will be for finite dimensional Hilbert spaces rather than infinite dimensional, since they mainly capture certain topological environments that make it discrete and finite. And that's also the crucial part that make many mathematical or physics concepts mathematically well defined, like the state sum becomes the finite sum. So it becomes very powerful in that sense. And then as an advantage, people can study this theory using certain axioms in their approach, like the category theory and also a kind of quantum version of the homotopy theory. And then we don't really need functional analysis in that sense. And we can avoid a lot of interesting analysis, but somehow we still get the interesting topological environments from this theory. But now in this talk, I want to say, even for this kind of finite dimensional approach, still reflecting positivity is extremely interesting. We shall not give up that condition. There are some reasons to people forget that condition, because if we give up that condition, then we can work on this theory on arbitrary field rather than this complex number field. Then this will work in like different ways, like for arbitrary field, even like finite field, or even like periodic number. So that has other reachable theory. But here we'll see what's the very interesting part that we learn from reflecting positivity. The topological invariance of Witten can be rigorously defined using the Lincoln invariance from representations of quantum group and the Licorice-Wallace surgery theory. And this is done by Reshetik and Tverev. So now it's known as the Witten-Reshetik and Tverev TQFT. And essentially, just from the representation theory of quantum group, we will get those representations with gradients, and they are captured by the modular tensor category. And then Tverev and Vera used the modular tensor category constructed another type of 2+1 TQFT using a state sum construction of triangulation, which is kind of a combinatorial analog of the passive integral. And then Barrett and Westbury realized that in the state sum construction, we don't really need the gradient, so it just works for the fusion category. So without gradient, it's no longer a 3D diagrammatic computation, rather it becomes a 2-dimensional computation on plane, captured by a spherical category. And this construction of Tverev has been generalized in 1-dimensional higher in 3+1 case, using the gradient tensor category by Kriniater or the fusion 2 category by Douglas and Reuter. And the theory is really very rich. One crucial reason is that in this lower dimensional case, we are not lack of examples, since we have a huge amount of groups, Lie groups, quantum groups, of algebra, vertex operator algebra, compound field theory, there's many sources to produce interesting representation theory, which gave us this kind of a fusion category or modular tensor category. So it's totally fine. We take this as an axiom and study TQFT from this categorical point of view.
So the fusion 2 category only appears in 4 dimensions?
Yeah, fusion 2 category will give 4 dimensions. Fusion 2 is essentially a 3 category with 1 object. And that gives a 3+1 TQFT.
You're going to explain what a fusion two category is?
I want to explain that.
Okay.
Yeah. Instead, I will give another. Later, we will see another definition that's equivalent to this one.
Very roughly, the fusion two have a particle and a string.
Okay.
And then to study the higher dimensional TQFT, Boyce and Dolan proposed a topology hypothesis to study the theory not just the codimension one boundary, but the all higher codimensions, and capture that as a monoid N category, symmetric monoid N category with a fully dualizable object. And this has been proved by Lurie and Hopkins on dimension 2. And in higher dimensions, we studied this very fruitful theory of the infinite N category as kind of a quantum version of the homotopy type theory. And that to study this non-invertible higher symmetries and about this topological hypothesis. Now, but if we look at the construction from representation theory, it's not really from an N category to an N dimensional TQFT. It's from an N category to an N plus 1 dimensional TQFT, or N equal to 2 or 3. And that construction has been widely believed that it should work in all dimensions. Because if you start with a unitary or spherical N category, you should get N plus 1 dimensional TQFT. And also there's another very interesting connection to topological orders. Just from the unitary N category, we should be able to get an N dimensional topological order, and then N plus 1 TQFT, which characterizes symmetry. So this is kind of a general guess or general principle we all believe, but there are some problems, like what is the mathematical definition of those kind of N category? For the ordinal N category is fine. You have 0 morphisms and 1 morphism, and the morphism become like among that you get just from 0 to N. And the graph looks like a rectangle. Just once you add one more direction, you just go to one more direction, orthogonal direction. But to get a spherical N category, you have to make this rectangular shape into a sphere. Then it becomes very complicated. Like in the 2 plus 1 series, you have to have this evaluating the kappa and cat, and then describe the zigzag relation. That's the one actual condition you need to check. And then in higher dimensional case, you need to check all those kind of singularities coming from Morse theory. And that's very, very complicated. That's why it's so difficult to give the mathematical definition. And for the 3 plus 1, like for fusion 2 category case, they indeed consider all possible moves and reduce all the relations to finitely many and describe this pivotal condition, like for hemisphere and another hemisphere and the saddle surface. There's all the relations among those kind of surfaces. So you can imagine this in higher dimension, you have many building blocks, and to describe their relations in a consistent way would be quite challenging. So that's why it's getting so difficult to give the proper definition in that sense. And another very important question, found one-to-one in topological order proposed by Xiaogang Wen is just they understand how to characterize topological orders using the categorical symmetry. And this has been widely studied for over 20 years. But from the view of condensed matter, it should be more natural to describe the topological order just using the ground state or using the Hamiltonian. In that sense, we don't really know the categorical symmetry ahead. So this is the kind of, we can study physics using Hamiltonian or using partition function or using symmetries. And symmetry is just one way to learn that. And there should be other parallel way to learn that. So how to describe those topological orders just using ground state? That's another challenging question. And then all those kind of concepts has been well developed in the lower dimensional case, in particular in 2 plus 1 case, because everything is pretty clear. But we expect just those framework should be also true in higher dimensions. And actually, even in 3 plus 1 case, many things are unclear at this point. And somehow just the 4-dimensional topology is already extremely complicated. And in particular, where do we find such kind of examples of higher quantum symmetry or higher category rather than take them for free as axioms? In particular, if we run this machine, we expect to get a higher algebra, maybe some higher analog of like top algebra or quantum groups, and to get some higher representations. And then the representation should define a higher category. And we expect the higher category should have the unitary condition, that means reflecting positivity, also spherical conditions, so that we can construct the higher dimensional TQFT. So we expect to fulfill this line. And all the red arrows are open questions, and all the red terminologies are actually even open for mathematical definitions. So now we give the solution to this chain. The first, we take a linear function of Z on labeled stratified manifolds with support on Sn. So you can consider it in this way. You have an underlying space that's the n-dimensional sphere. And then you have a stratification that's kind of a lattice on the n-dimensional sphere. And label just means at the set, like 0 cells, you have those labels given by spins, like qubits, or just more general spins given by vectors given for fixed vector space. And then we expect that this linear functional will have 3 properties. The first one is reflecting positivity. So what's the meaning of that? For the sphere, you can cut the sphere in the middle. And in constructive quantum field theory, you consider that mirror as a time 0 space. And then you can look at the past, the half time sphere, and the future, the other half. And then you can take the reflection from one side to the other. And when you glue them together, you glue the 2 disks and disk to a sphere. And then this linear function will give you the inner product between 2. And reflecting positivity means this inner product is positive semi-definite. And that means for the boundary for the disk, it forms a vector space with a semi-positive inner product. So the torsion space will be a Hilbert space. And that is a physical space in quantum field theory. So in this way, we really want to study this physical space coming from this lattice model. And then what's the meaning of continuum limit in this case? So we fix the boundary, but then we don't fix the shape of the lattice. We can refine the shape of the lattice in an arbitrary way. And in that sense, we can consider limit, meaning we consider all possible lattices. And after we take enough lattices, then we have the full space. Say if it is finite dimensional, then after a certain limit, then at a certain step, we get to it. And this is kind of the analog of continuum limit. And the very interesting part is that from this limit, we can read a lot of non-trivial information as an emergent phenomenon. And the first emergent phenomenon is following. Yeah.
So when you do this manifold, you mentioned you have index on the vertex.
Index.
But you have index on the edge, on the trunk, on the face, whether index on every cell or just on the vertex.
At this point, we just take the index just on the vertex. Okay. If we want the index on edge or face, we just put another vertex on the edge of face.
Okay.
So we don't lose the generality in a sense. The reason is following for the index on edge and the face, they should correspond to certain colors. And for 2 different colors when they meet.
Yeah.
That should be a delta function. But we don't mention that here because we will show this kind of color is emergent.
Okay.
That's really the higher idempotent or higher representation of the color, or somehow the higher particle in that sense.
Yeah. So this is different from the state sum. State sum formulation usually have index on every.
Yes.
Here is different.
Yes. Okay. In that sense, the state sum comes from something we already know how the particle behaves like.
Yeah.
That's the n-categorical structure. Here we say even before that, we don't know the existence of such particle. But what we know is the existence of certain functional integral. And then we rate the particle as an emergent phenomenon. It's kind of a condensation phenomenon. Now, from this linear functional, the reflection positivity is crucial in this case. And another condition is homomorphic invariance. That means for the lattice, we can translate lattice in any way we want. It's a diffeomorphism. And this linear functional should be invariant under this diffeomorphism. Like usually in the quantum field theory on the flat space, it's invariant under like translation and rotations. But here it's invariant under homomorphism. And that's the key part, make the theory topological. So if we somehow give stronger restriction on the symmetry, then we have different kind of theory. But here we will talk about the topological version. And the third condition, the complete finiteness, and that's really a mathematical condition just to ensure everything is a finite sum. So that's not really a physical essential condition. So in principle, just the first two conditions. The first one is analytic. It's kind of real functional integral point of view. The second one is topological, it's homomorphic invariance. And somehow just when we combine the two together, and all the magic just happens. So from this linear functional, we will first read out a vector space that's a disk with boundary. And what do we mean by a disk algebra? Just for two disks, we can glue them together and get another disk. So in that sense, we can glue them in all the ways. So in that sense, we get an algebra. We call that a DN algebra. And then in general, you can get just free algebra without any relation. But since we have this linear functional, if we look at the quantized space, then we take caution by a very, very big space. And the caution algebra becomes extremely interesting. That's where we get to this non-trivial condition. And after we have the caution algebra, then we look at the idempotent of this algebra. And that's kind of the higher representation of particles in higher dimensions. And then we get those high representation theory. And then we can look at the interaction of the representation or interaction of particles. Like if you have two k-dimensional theory, and then the domain wall between them is a k-1 dimensional theory. And in this way, we just read it step by step. We get the theory in all dimensions. And that's how we get interactions of this different kind of dimension theory, and also mathematically characterized by a n category. And since the theory has reflecting positivity, the category is unitary. And since the theory is defined on sphere, the category is spherical. So we learn the two conditions this way. And there should be a more general version, since here we are taking the sphere without any additional condition, like orientation or other spin structure of frame. So there may be additional requirement, but here we are taking the best condition and try to simplify the terminology. And then from that one, we run a similar machine like the say sum of 12 0. Then we get a n+1 TQFT. But we not just get the ordinary n+1 TQFT. Here we will get an even bigger one. That's what we call Alterfold TQFT. And this Alterfold means the TQFT has an alternating color, A and B, in the top dimension, n+1 cells. Yeah, and why that color is important, because the original n-dimensional theory we start with will be the domain wall between the A-B color theory. So that means in this theory, when we go to one dimension higher, we do not lose any information. So everything is there, we don't lose anything. So in that sense, when we go to the higher dimension theory, it just becomes more and more interesting. So we won't see this kind of, in some sense, if we don't look at enough information, then sometimes the higher dimension topology could be easier than lower dimension topology. But in this approach, that's not the case, since we are considering all the stratifications.
Is the homomorphic invariance related to retriangulation?
Sorry?
Retriangulation, the second invariance.
The second.
You have this, usually I say this S3, Sn is triangulated, but you may have different triangulation.
Yes.
It does relate to the second condition.
But yes, that's related.
Retriangulation.
Yes, that's related to the second condition, retriangulation. This homomorphic invariance is slightly stronger than retriangulation, and that's actually a phenomenon we still don't fully understand. If we just use retriangulation mathematically, we can see a gap in the truth. And here, this stratified manifold will overcome that gap. So our functional integral construction suggests the mathematical definition of the unitary and spherical n category. And in this approach, we do not take this n category as an input data to construct the TQFT. Instead, this will be an emergent symmetry. This is really in the favor of condensed matter. It's an emergent phenomenon. And this categorical structure really comes from the physical quantized space after we take caution by the kernel of the partition function. And the three conditions provides this recognition of the linear functional provides a characterization of topological orders and from its ground state, which it gives an answer to the question of Xiaogang Wen. So you may wonder, how do we relate this linear functional with the ground state? And the answer is actually rather simple, since the underlying configuration space is a Hilbert space. And then every linear functional is a vector state in the vector space, is a vector in the wave function in the vector space. So just by this duality, if you consider linear functional on all kinds of lattice, that means in each lattice, you are choosing a vector state. And in particular, if we are working in the framework of topological orders, and that vector space state should be the ground state.
So if I imagine this linear functional should satisfy these three conditions.
Yeah.
But the solution of the three conditions, are they discrete? Or there's a continuous solution and then you have to push it out more?
I would guess it's discrete, but the proof should be highly non-trivial. In two-dimensional case, this is the rigidity theory.
Oh, I think.
Just given first for the finiteness, you are given a fusion ring,
Okay.
and then given a fusion ring, you have only finitely many fusion categories. So that's a
So
rigidity
here you're
theory.
thinking maybe discrete.
Maybe discrete, but it's not.
So in a sense, okay, no, I see. So in a sense, this linear functional you mentioned is like a wave function.
Yeah.
But the wave function is kind of like we call a fixed point wave function already.
Yes.
Yeah,
a
already
fixed of
kind of,
amplitude. Yes. Oh, by the way, so here, since I don't know the kind of those color I need ahead, there's no way to define RB flow in that sense.
yeah.
And the interesting part is this partition function, it will induce the inner product between one lattice and another lattice.
Yeah.
They may have a different shape. And this identification will define the RB flow. So very important idea is the following. Because in physics, we know that once we know the partition function, we should know everything. And somehow we implement this principle in this work. Because we just know this linear function or this partition function at the beginning of the lattice model. And then from this caution by the kernel, we learned many other structures, algebraic structure, categorical structure, and topological structure, and get to the TQFT. So all those are emergent phenomena in the limit. And now I'll give you a one-dimensional theory, 1+1 theory to see what we are doing. So in one-dimensional, it's just a line, and then its stratification means we have like the points that we can put the spins. And then if we just have a line and have the spins, then essentially we will have the direct sum of the tensors of this vector space of the spins, and that's the Fock space. And then if you glue the two disks like D1, it's just a tensor product of the vector space, and that makes the Fock space into an associative algebra. And this is just what we did, just make the additive theory to a multiplicative theory. It's a usual process. And then the linear functional is just like a linear functional on this Fock space. And reflection positivity means it's a state. And the homomorphic inverse means you can rotate this on a circle and it's inverting that way. That means this is a trivial state. So in that sense, once you have a trivial state on this algebra, then you can run the alpha 9 maximal construction. And you take Cauchy space and you get a C-star algebra from that, or von Neumann algebra from that. And then this finite condition really means this von Neumann algebra is finite dimensional. So that's just for the computations. And certainly we are happy with infinite dimensional examples, but just technically to ensure this is rigorously defined, we require this finiteness condition.
Where did the fact that there's a Hamiltonian with a gap come in?
Yeah. So the Hamiltonian, then here I take linear function, I give you an example. If we take, say, the Ising type of Hamiltonian, the Z1, Zi times Zi plus 1, and take the linear sum of that. And then we can read the ground state. And the ground state will be just 0, tensor of zeros plus tensor of 1. And then we can consider that as a linear function. That means just for the arbitrary spin, you will get value 1 if everything is 0, and another value 1 if everything is 1. And in that way, you will reduce this Fock space to a two-dimensional algebra with just a 0 or 1. and you get two pure states that's corresponding to 0 and 1. So that's us the Ising will eventually just give us a two-dimensional algebra. And if you change the kind of the ground state, since it's not unique in this sense, if you change the parameter to after 0 plus beta 1, it's just a kind of convex combination of the pure states. So just once you have a Hamiltonian, you can read out the ground state. And from that ground state, you can find this kind of linear function. And actually, there's another interpretation. We actually don't have to take the ground state. We can really consider this e to the minus beta h, this Hamiltonian, as a evolution. And then we can take that acting on boundary condition or initial condition, and eventually we get a solution of the PDE. And that solution, we expect that solution has reflecting positivity if the initial one has. And that's somehow indeed the case. And then that's
It sounds like you're assuming that the ground state is a trivial product state.
yes, in this case, yes. Just in this one-dimensional theory, it's just the pure state is the trivial product state. There's no non-trivial one-dimensional topological order without symmetry. But in the next dimension, it becomes highly non-trivial. And later we will see the Torrey code. That's the example in 2+1 theory.
But you can get things like Haldane gap, which have edge states and so on. You're not interested in those.
So far, I don't see since just I was wondering what's the difference between gap Hamiltonian and gapless Hamiltonian. But in this approach, I don't see this kind of difference so far. There must be something more crucial to the theory if we just look at gap theory and gapless theory. But I'm not sure about that here.
I wonder whether the wave function can track, because you have this homomorphic invariance. So somehow it has no sense of distance.
Right.
It's kind of topological.
Right.
So if you don't know the distance, so probably that's means
Yeah. Exactly. Just in this theory, if we take the Hamiltonian, the local term is independent of the distance, and that makes the theory topological. And if the local term, the local interaction depends on distance, then it will not be a topological theory.
Well, that's you hinted here. You know, after this construction, you get some kind of von Neumann algebra in some don't reach type. But it seems that suggests it's a von Neumann algebra. It's naturally tied to the one-dimensional theory.
Yes.
And then that suggests that if you do two-dimensional theory, actually it's different algebra.
Right.
So, okay, yeah. So because from von Neumann algebra, get the subfactor, get the fusion category, it's a 1D theory. But it's kind of mysterious how the dimension enter.
Yeah, that's puzzled me for more than 10 years. Now I can give a very happy answer to that. Why subfactor theory gave a 3 manifold invariant in the work of Jones? The answer is following. First, the von Neumann algebra is a one-dimensional theory. Subfactor is the inclusion of von Neumann algebra. And you can consider that as an action on this one-dimensional theory. And then that action is two-dimensional. And then for that action, you will have a cocycle obstruction. That is three-dimensional. And actually, in the early work in 1970s, Alan proved that all the group automorphisms acting on Hamiltonian factor for a cyclic group is classified by three cocycles.
Okay.
And then in one thesis, PhD thesis, it generalized that result to finite groups. And later it generalized to compact group by Occhiani and middle group by Uberhagen. So that's the magic three cocycle in that theory. And here it indeed has a very explicit meaning. And if we reduce that one dimension lower, that means we have a group action on the vector space. That's classified by two cocycles.
Yeah.
If we increase the dimension one dimension higher, then we have a group action on fusion category. It's classified by four cocycles. All the
Dimension
dimension,
enter here.
yeah, dimension really enter here. So that dimension I would say is really the physical dimension.
Yeah.
So in a 1+1 theory, so we get something very simple by the end. If it's a 5-dimensional theory, the action is 6 dimension, the cocycle is 7 dimension. It goes in this way.
Okay. Yeah, nice.
Well, but that statement so far is still conjecture. And there are many, many details. So this, if you are interested in that, I can explain further details about it. So for one dimensional case, what we have is an associative algebra, a finite dimensional with a tracial state. And then say that means for the minimum idempotent in each component, we have a positive trace with dj. And then how do we get just from this kind of a very simple algebra? How do we get a two-dimensional topological quantum field theory? At least we should get a two-manifold invariant. And we can get that in the following way. This is one-dimensional theory on a circle. Now we first we consider a circle as a boundary of the disk. We fill the disk as D color, the dot color. And the outside part is A color. You can consider A as a vacuum, B color as something like a gravity. And then we have all algebraic structure on the line for all the associative algebraic structure. And now we putting that on the circle as boundary of disk. Then we can put many disks on the surfaces, just colored by A and B. And then we can find additional relation. Just if we have this kind of double line, it's kind of a thick graph of the one skeleton, B color one skeleton. It's a micronormal bundle. And then you can change the shape of that. And the right side is kind of you can consider this and the vertical multiplication. This is really the identity map. And the right side will be a bracket notation. This is really the resolution for identity of one-dimensional algebra.
Here we're trying to understand what is ZSB, ZSA means.
Oh.
Does S means it's a circle?
I'll explain that. So S is the surface, and B means
SB is a circle.
S is the surface, and B means the surface is fully B color,
Okay.
and SA means it's fully A color, and Z means the corresponding value. And we will show their quotient is involved.
So SS is the surface. And then you mentioned that you have something defined on one dimension, which is with index.
Mhm.
How that also appear in this formulation?
Oh, here the index just means it's PJ. Once we have the idempotent completion, then we can label the one-dimensional cell by this minimum idempotent. That's the role of idempotent completion.
So here, in this one, you have A and B, that two surface, and the boundary of a PJ, that is the index you're talking about.
Yes, yes. And then the first relation is just how we evaluate the value of circle as a boundary of this. And second relation is the resolution of identity as the one-dimensional algebra. And once you have the second relation, then you will see an interesting phenomenon. Just if you have two circles labeled as Pi and Pj, and when they meet together, you will get a delta function delta ij. So this circle labeled as Pj is also minimal idempotent, but in the two-dimensional algebra, because you take multiplication on the plane, that becomes a minimal idempotent. And then the last relation is a resolution of identity in this two-dimensional algebra. So all those relations are just a resolution of identity of the corresponding dimension. It's kind of a decomposition into this single particles, the state of relations. And then once we have a relation, then what's the topological meaning? Topological meaning is, first one is if we see a neighborhood of a point, a B color point, we can remove that. The second one is if we see a neighborhood of a B color line, we can remove that. And the third one is if we see a neighborhood of a B color face, we can remove that. And that's all we have for the two-dimensional case. So once you have a triangulation of the 2D surface, you can run the three relations and remove everything from B to A. Eventually, you end up with the surface of A color. And in that way, you get an invariant. Of course, we need to show this computation is independent of the triangulation, independent of the choice of relations we defined. But finally, we know this gives the invariant. And in this case, if we run this machine, then the invariant has this dj, this dimension of minimum idempotent, to the power. And if you just count the coefficient, it's just +1 -1 +1. And if sum over the power, then you get according to the number of vertices and edges and faces. And that's exactly the Euler number. So in this case, a two-dimensional TQFT gives you invariant of surfaces, which is dj to the Euler number, summing over of j's. And clearly this is invariant. We all know this invariant, the Euler number is the invariant of surfaces. That's just what we learned. And this machine, this works really in all dimensions. Just this argument just goes through all dimensions. And then we can get this kind of TQFT in all dimensions just by starting from a theory on Sn and fill the bulk as a dn plus 1, the disk, and then glue all the disks together. And this kind of gluing is a factorization process in algebra topology. And this is a quantum version. Now, for two-dimensional case, 2 plus 1 theory, we can take detect story code. And it's a two-dimensional lattice models or square lattice. And we can define the Hamiltonian and the local term as sum of local term, the vertex operator given by product of poly Z, and bracket operator given by product of poly X. And then we can look at the ground state. We know this has 2 logical qubits as the ground state. It has degeneracy. And to get a theory on the sphere, not the torus, this is theory on torus. To get a theory on sphere, then you will see the ground state will be unique. And then we have to change the lattice. Since the square lattice won't be put on the sphere. But this model can be generalized to lattice of arbitrary shape on arbitrary surface. And then for on sphere, the ground state has the following form. It's just sum of all the configurations such that the label 1 edges forms loops. So we just call it sum of all possible loops. And then if we take that ground state as a linear functional, then what's the meaning of that? That means if you look at those configurations on the sphere, and then if all the spin 1 forms a loop, then its value is 1. Otherwise, its value is 0. So it's just counting the number of loops labeled 1. And then from that, you can read out, just from the algebra, you can read out the 2-dimensional algebra, what Jones called planar algebra. And you can read out the fusion category, that's 2-dimensional. And that's the representation of Z2 or vector Z2. And if we modify the lattice a little bit, just refine the lattice using this 45-degree thing, just it has the same kind of position of spins. And the local operator, vertex operator, and bracket operator both become bracket operator. Then the primary one is this duality will become a symmetry, a translation symmetry. And from that additional symmetry, on the categorical level, we will find indeed additional non-invertible object. That's the Ising type symmetry. So this is a way we can use this modification of the lattices to get from a group to something non-trivial outside the group.
Can this need to be promoted to some like non-abelian group or other things?
In that sense, it's not. This Ising symmetry is a Z2 graded extension of this Z2. So that's the meaning of Z2. That's a Z2 graded extension. So it's really a Z2 gauging theory. The Z2 gauge theory. Not. This will be a little bit confusing at this point. That's a gauging in another science. This once we refine the lattice, then we will have this kind of Ising symmetry.
But like, can this linear function for different symmetries can be defined for different symmetries? Like
Yeah, they can be defined for symmetries. It will be on the next page. Since this one, we will see the Hamiltonian, the ground state, everything clearly in a closed form. And the generalization, the small general version will be the Liu model for the spherical fusion category. And in general, we will construct Alterfold TQFT. And Alterfold just means given a manifold, we have one additional separating surface. And on 2 different sides, the cells are colored by A and B alternatively. And you can just imagine this hypersurface is where the lattice model, n-dimensional lattice model lives on. And the AB color is for n+1 dimensional cells. And eventually we want to extend TQFT. RTS TQFT is from cobordism category to vector spaces. So this will be from the category of cobordisms of the section of orbital, the cobordism with additional separating surface. And then everything else is just the same. So this will give you additional structure in the TQFT. That's what we call Alterfold TQFT.
So in this A regime, B regime, do you also have a triangulation? You have index And where's index are also on the vertex?
So first, in the bulk of A and B,
Yeah.
A and B themselves are just the color. So those are the A, B are just the index in top dimension.
Okay, and
we
but
don't
there's
have-
no triangulation or there are triangulation in in the bulk.
In the bulk, when we show this partition function is well defined, we need to take triangulation
Okay,
in the bulk.
but this triangulation, once you take triangulation, do you have an index somewhere?
Yes,
Okay, that's
Oh.
also on the vertex.
yes, the index will live on the boundary surface,
Only, but not in the bulk.
not in the bulk.
I see.
And then the boundary theory comes back to the previous theory,
Yeah,
and it's there.
but if there's no index, so why do you need the triangulation? Because then you don't have anything in the bulk.
Oh,
The bulk have no
because
index, there's nothing there.
Originally, we only have the value on sphere. We don't have the on disk, n+1 dimension disk. We don't know the value on n+1 manifold. Then we have to glue the disk together. And when we glue the disk, we may end up with a n+1 manifold, but there are different ways to glue them. So that's kind of different triangulation or Handel decomposition. So we need to show the consistency of those kind of gluing maps. And in particular, just we have the A and B color, and in previous series of TQFT, either we see B color or we see A color. So we see one of them. And this is kind of an interesting duality between the two. And if we shrink B color, then if A color is outside, then this is more like the tensor network. And if we shrink A color and leave B color outside, this is more like the center. And later we will see this is actually in a 2+1 series, it's a Greenfield center. And actually, add one more comment. When I first saw this structure in the QAnon language, we started quantum information with us. And we described the tensor network using a blow-up picture that has surfaces and with the interior bulk. And I don't understand it at that time, just why we have those three manifolds inside, what's the meaning of that? And since tensor network always lives in R3, so we don't really need three manifolds. But then later we realized this really works fully in 3 dimensions. And that gives quite new interesting results, even for extend the pure language for quantum information. Now, for 2+1 case, the ABC are indeed quite interesting. In particular, we show that if we start with a spherical category, and then if we take the Z, just let it say just a straight net on the sphere, and the linear function of Z is the evaluation map of the straight net in the category. And then in recent work done with Shuangming, Yilong Wang, and Jinsong Wu, we prove that this Alterfold TQFT will contain both the famous 12-0 Barrett-Weisberg TQFT and the Witten-Reshetin 12 TQFT of the center. And for the first one, the Witten-Reshetin, 12-0 Barrett-Weisberg TQFT is defined based on triangulations. And in our case, we can blow up this skeleton of triangulation such that it has B-color channels, B-color interior. And then we can embed that TQFT in our theory. And for the Witten-Reshetin 12 TQFT, it's 3 manifold with beams. Then we blow up those beams with A color inside, and we can embed that TQFT in our case. And in particular, if there is just no decoration inside, just manifold, and then we can look at the series just for topologies, that's a TQFT. And that will be a sub TQFT of both. It takes really a long time to show the sub TQFT of both are really identical. And actually, it's proved as a not identical, but they are equivalent. There is a function from one to the other. And here we can show they are identical since we can embed both in a common bigger TQFT. And they're just the same in their case. So it's stronger than it's to be equivalent. And this really has a long story. It's first observed by Kevin Walker for the SL2 case. And then generalized to model tensor category and proved for unitary spherical fusion category. And then proved for general case. And it takes about 26 years to get to the final proof of this theory. And in our case, it becomes it's a very quick result. 2 different ways to compute the partition function. One by triangulation, the other by surgery. And they have the same result. That's it. Now, in particular, to encode the surgery theory, we take the manifold with A color to have partition function constant 1. And that means the theory is irrelevant to the shape of the A color part. So we can actually change that. That's how we dig up the A color body and then fill out with another one. That's how we run the surgery theory in this world. So in that sense, we call the A color to be the trivial color or something like the vacuum, even though it's not really that trivial. This actually is very useful to describe the lattice shape in the last matter. And the B color, we consider that as a one-dimensional higher center of the n-dimensional model, the box center. And if we run this construction twice, then somehow we won't get the interesting n+2 manifold inverse because the n+1 theory has a trivial A color. So we can do all kinds of computation from the A color theory. Then we get from the trivial theory to the trivial theory. And this has been interpreted as the center of the center is trivial. So there's also a long story about that. Now, since we can embed the two TQFT in the bigger one, actually we can embed many other concepts in this very, very big Alterfold TQFT, even for the 2+1 theory. This is already interesting in 2+1 theory. And there are several kinds of embedding theory in subactivity, like from plane algebra to graph plane algebra. And another one is called alpha induction related to conformal field theory. And another one is characterizing the ground states of library model, just embedding the ground states to the configuring space, all kinds of embeddings. Just all those kinds of embedding can be uniformly characterized by a simple fact. Because if you are on a two-dimensional theory, you just take a parallel space just without decoration on the other side. This is just obviously embedding map. In those kind of sense, just it's embedding map. And all of them are just like that, just with different interpretations. So this gives a uniform interpretation of such an embedding maps. And once we see this point, actually, we want to see what happens if we reduce this one dimension lower. Then that gives the alpha 9 Mach single construction of the dy of the operator. And if we go this one dimension higher, then it's just completely new. We don't really know how do we interpret those kind of embedding map in one dimension higher. But somehow the theorem is there. It just needs a better interpretation. So now we have obtained n+1 TQFT from this linear function. Somehow n-dimensional lattice model, more precisely labeled regular stratified piecewise linear n-manifold. This linear function has three conditions: reflection positivity, homomorphic inverse, and a finiteness condition. So we propose this program on this functional integral construction of TQFT using such a linear function. And also we propose new methods to construct such linear function. And there are different ways to consider this. One is that the linear functional can be considered as a path integral. And there are other one is this can be considered as a ground state of a Hamiltonian. And the third one is considered as just an evaluation map in a higher category. And we have seen such kind of examples. Now I will give a new example. As we run those ideas in 3+1 theory, somehow we can take the 3+1 trivial Z2 gauge theory and the lattice model. And then we just run a similar trick, like in 2D, we change lattice, we refine the lattice shape. In 3D, we can do a similar thing. So originally it's a horizontal one. Now we take the lattice like orthogonal to the normal vector, like 1, 1, 1. So we have 4 families of parallel physics. And after we take the refinement, we get another lattice. And then from that lattice, we can look at ground theta and define partition function. And then the partition function is like this form. So you have surfaces, now have surfaces in S3. And those surfaces will give you the value. Each surface contributes to this number 2 to the 1 minus its Euler number over form. And in particular, the value of a sphere is the square root of 2. And that's kind of the quantum dimension of Ising type non-invertible object. And the value of a torus is 2. And that will decompose into two one-dimensional particles.
Yeah, so here I'm confused about, you have this three sphere, that would be a dimension, three-dimensional space.
Yes.
And then there's a triangulation on three sphere.
Mhm.
And then there is an index on the vertex. So this function is a function that depends on this index. But this one don't have index.
Yes, that's the part that's really the missing part. This one has no index. And that's really the missing part in lattice model. It's just in lattice model, we will see how to define the partition function on those decorations with index.
Yeah.
But that's not enough to get to TQFT. There's additional data.
Okay,
That's a partition function on those kind of surfaces without index.
without index. Okay, then so this is just a part of this linear function. There's another part which is with index.
Yeah, if we can have additional series with index, but this is kind of like in the template Jones case. It's just value of circles without index.
Yeah.
Yeah.
First, we have in general, we have index. And there's a lot of condition, and you have this some portion, I think. But at the end, from those conditions, you find somehow you need to also define this linear function on the space without index.
Yeah.
And this is just a very small piece of linear functional without index. But there are also a piece with index.
It includes everything with index. The
But
index
there's
here is
no
the following.
index. That's what confused. You know, there should be, suppose you have a sphere, triangular by tetrahedron. So three triangle, or maybe that's a two-dimensional sphere. Whatever, you add a few spheres, then there's still index.
Yeah.
So what is the linear function of with index?
Yeah, I will
What
show
is
you,
range of
I will show you immediately.
Let him continue because,
Just next page.
Yeah.
Just next
Okay,
page.
okay, I see.
Just okay, go to next page and then come back.
Sure.
Just if we fix the boundary as two circles,
Yes.
if you shrink a circle to a point, this is really just a spin on line, but we blow up them to the boundary disk. And then this spin on this edge is two-dimensional.
Okay.
So the basis is the following. You have two disks with two boundary circles. That's one vector. All this kernel, that's another vector. And this vector space is two-dimensional. Those are the spins. So that means if you write the lattice, and if you put a spin on the edge, then essentially you are putting the two pictures in there. And then for the vertex, you have to blow it up. And then there's no singularity. It becomes just a smooth surface. So eventually for the lattice with spins, it's given by a linear sum of surfaces in the sphere. And that's why the previous linear functional already includes this. It includes the linear functional on the lattices labeled as spins. Yeah. But one thing was very surprising to us is we found this right linear functional. And then when we compute the categorical structure, we don't get a finiteness. Actually, we get infinitely many one morphisms. And then we see if we allow the surfaces to intersect, then it reduces to finitely many. And this becomes kind of something we didn't expect at the beginning, but it works in this way. So once we allow the surface to intersect, then we get the right answer to construct the TQFT. And what do I mean by one morphism? One morphism, zero morphism is just the background color in the 3D space. One morphism means the domain wall between those planes. And then how do you compose them? Just take parallel faces with a composition of one morphism. And then you can decompose that. So this will be kind of identity times identity. And then it's the identity in the multiplication in this two-dimensional direction. And the kernel is also identity. You multiply two kernel, you see a hole in the middle. But by the previous linear function, you will see a relation. But you can remove a handle by multiplying a scalar 2. And then you see this relation. And
So-
then that will be a sub-idempotent of the first one. So their quotient is also idempotent. So this is kind of how do we do idempotent completion. We just find all the minimal idempotent in this higher algebra. And in this case, this algebra is actually cumulative. So it's even easier. It's just not hard to compute. So now we have one just a single face is what we call top, and the double face will be top square. And this kernel means it's a morphism from top square to trivial. It's empty in the middle. And the rest part is the G, it's the additional morphism. And this G is invertible. G square is equivalent to 1. And the interesting part is if we take G tensor top, then it will contain a copy of top. But if we don't allow the surface to intersect, then it will have additional morphisms. It doesn't stop. And we will get infinitely many non-morphisms in that case. But if we allow them to intersect, we can reduce all the additional morphisms back to top and get the Ising type of fusion rules for one-dimensional variable. And then once we know the one morphism, we just put those one morphism on the boundary of the circle of the disk. And then we look at all possible things we can fill in the disk. And that will be the two morphisms. And we can write down finitely many. And then once we know two morphisms, we put everything on the boundary disk, on the sphere, decompose as disk. And then we fill the part inside. And then we get a three morphism, like this. And we fill the surfaces inside. And three morphisms will becomes, we get three morphisms, and then we fill them, we get the four morphisms. Those four morphisms. And for the four morphisms, they are vectors. And then for a boundary, we can change those vectors by changing our bases, like the symmetry symbol in the 2+1 case. Now it becomes 20J symbol, just given by the changing of bases. And then we can compute those values, the 20J symbols, higher analog of the symmetry symbol. And then you can expect the 20J symbol should satisfy something like the Pentagon equation. And it's the case. And topologically, that's called the Pentagon move. And the Pentagon equation is a 3 to 2 move. And one dimension higher, we have 3 to 3, 4 to 2, 5 to 1 moves. And we check them, and there are more than 50,000 of equations like that. And it's true. And I shall thank my student Nippon Wang for a lot of help on running this program, checking this computation, very challenging computation. So this really convinced us the series works well and the computation really works.
So there's in the state-time formulation, I think maybe there's also 20J symbol. And so whether the table you have 20J symbol and the state-time are they similar or related? But in the state-time, the 20J symbol is a full cell.
Yes.
You have the vertex, how many edge, how many face, so then it happens to be 20 on
yes.
Then
it's really similar, but what's the difficulty part? If you want to look for a solution of such 20J symbol by solving some kind of equations, first you already see the number of variable here is about 30, so it's hard to solve the equation. But even theoretically, it's also very difficult because we don't know the fusion rule. For a two-dimensional case, the fusion ring is very easy to describe. It has finitely many relations. For three-dimensional case, the fusion rule has infinitely many equations.
So here you're using this Ising fusion category somehow construct 20J symbol which satisfy those equations.
Yes.
Okay, understand.
This gives a way to find such kind of solution. So, and also when we do this computation, we also see this kind of function, this computation is irrelevant of the dimension. But in higher dimensional case, there are some very difficult theorem about the copolysms, classification of copolysms, very deep theorem. Tom, really dates back to 1950s. And we have to learn that carefully and using like the Whitney numbers to calculate the copolysms and really to give a rigorous proof. But somehow we believe this result really works in higher dimensions. In particular, in dimension lower than 6, there should be no problem since the classification of volumes under dimension 4 is just 1. But we want to see this result in all dimensions. So that will give non-invertible symmetry and TQFT in all dimensions. Now, let's give a quick conclusion.
You could go along as long as you want.
Maybe just another 3 minutes.
Another half hour is fine.
So we propose this new program to construct a meaningful topological quantum field theory with unitary condition in any dimension. And we want to consider this as a lattice model approach from a functional integral point of view. This is really kind of a combination of these ideas from different sides. And we can construct such kind of TQFT using this linear functional with the 3 crucial properties. At least 2 very conceptual physical properties. And we find this answer to win on the characterization of topological orders just from the ground state. And also we construct this Ising type unitary 3 category and the 3+1 TQFT, which is non-invertible with explicit quantity symbols. And after searching literature so far, I think this is the first example with those data quantity symbols. And with such quantity symbol, then we can compute the 4 manifold invariance as a state sum. And not just 4 manifold invariance, we have 2 nodes in 4 manifold. It's really a 1-dimensional higher analog of the nodes in 3 manifold. So here will be 2 nodes. And I hope this will give some new insights to the topology, in particular topology with smooth structure in 4 dimensions. And I should comment that we are considering in the piecewise linear category, but in 4 dimensions, that's the same as the smooth category. And another very crucial thing is, in this talk, I emphasize a lot of this linear functioning. But what I keep in mind is really the Hamiltonian. So I learned that the physics will be very happy with Hamiltonian. So I know if we just say the linear functional, it seems not really a complete story. So it should be more fundamental if we go to the Hamiltonian. Then how do we consider that? If we take the Hamiltonian H, and then we take the action of e to the minus beta h, this is kind of a passive integral. And then acting on boundary condition omega. And then the final result will be the linear function. And in the previous approach, like in Attia's original paper, he mentioned that if we consider TQFT in terms of Hamiltonian, Hamiltonian will be 0, even though the Lagrangian is non-trivial. That's how we get non-trivial topological properties. And also in topological order, we usually consider the temperature to be 0, or inverse temperature to be infinity. And then you see in this theory, when multiply them together, they're actually the same condition. So in that sense, we are looking at this theory using the ground state Z. But if you look at the 3 conditions, we never assume it has to be the ground state. And actually, if the omega has reflection positivity, if it's a product state, and if the Hamiltonian also has reflection positivity, then this action, the result is also has reflection positivity. And if both have homomorphic inverse, then the action also has homomorphic inverse. So in that way, we get a huge amount of interesting examples. So that I would expect there's all kinds of linear functions already in this way, from this kind of passive integral in a more physics sense, will give such kind of TQFT. Then I'm puzzled. If that's true, then it seems that we have too many TQFT. And one thing I consider as an obstruction is this finiteness condition. And that makes it discrete. And then until recently, we realized there are some other very delicate detail about these conditions. And those are the definition of linear function, not just on the lattice labeled by spins, but on the lattice without spin. And those are kind of missing data we still don't quite understand. Those are kind of non-physical information. But there must be some interesting interpretation. And in particular, in joint work with Arthur, we have a very quick, not just very nice proof showing if Hamiltonian coming from certain local operator, it's a machine to prove the Hamiltonian has reflection positivity.
Positive Fourier transform.
Yes, just positive Fourier transform. And then we can just use that property here, and then to get a reflection positivity in a very general way. But after checking the detail carefully, this only works on connected component of lattices. So if the lattice have different connected components, that may break reflection positivity. So that's another phenomenon we don't quite understand. Since usually when we consider lattice model, we consider a single connected component. Because there's something in addition to that. And another remark is this theory is topological. And because if we really consider Hamiltonian, the Hamiltonian is given by local terms, which is independent of the matrix. Like for topological, We just look at local shape and take the tensor product of polys. It doesn't matter how far away the two qubits are the lattice. But in general, if the series is geometric, the interaction should depend on the distance. So that means the partition function will have two terms. One is topological term like this. The other is term depending on the measures. And in that way, we will get more interesting field theory with geometry. And we can expect that kind of theory will lead to the study of quantum gravity. Thank you.
Well, thank you for a really inspiring talk. I'm sure there are a lot of questions. There are questions in the room?
You constructed some TQFTs in 3+1 dimensions then?
Yes.
These are new ones or old ones or?
I think these are new ones. We check the data with known examples. And even for the number of like one morphism, two morphism, they don't coincide. And for the other papers, so far, we don't see the 20 symbol, so we cannot compare in that way. But just by checking those number of just the label of morphisms, they are already different.
Well, actually, really question. For this this Ising 3+1 can be constructed. This I wonder what kind of boundary and what kind of a boundary fusion tool category you may have. You know, you may have some very natural simple boundary which you know the fusion pattern. Then for the fusion pattern, there's questions about how many objects are they fused. What is the morphism of the things like that?
Yes.
So whether there's some knowledge about some certain boundary.
Yes. Just in the existing literature, I can see some constructions of those fusion tool using like Tori code and using like data orbital, and there are results like that. But it's actually surprising to me is when we check the data, they are not the same. That means even though from the same, like when I mentioned, even though we start with the Tori code in 3D, if we don't allow the surface to intersect, we will get a different fusion category with infinitely many one morphism. So I would guess just from a model, there may be like there may be different boundary conditions. There may be different ways
Yeah.
to write down the.
But for your model, do you have some particular very simple boundary condition where you know what is the boundary fusion tool category?
In this case,
Because you start from Ising, some kind of Ising fusion category, whether from this Ising fusion category can direct convert in the boundary fusion tool category.
yes, at this point we can see the somehow it's in this. So in the box, this the bullet and the empty will form a Z2, a 3D wax Z2. And then this is kind of the theory in the box. It's a symmetric tensor category. It can act on the 2D boundary. And the 2D boundary is what we mentioned as those one morphism. So in that sense, we can describe this.
Okay, yeah. So the 1 0 morphism and the 3 1 morphism, I see. So this is okay.
Yeah, this may be just
Yeah. So this just my understanding, I see this 3 1 morphism probably is like a string like extension
Yes.
on the surface, two-dimensional surface boundary. The 1 tau what's the T squared? Oh, I see T is Ising. Then what about the two morphism? Do you have non-trivial two morphism?
yes. The second picture, those will be the two morphisms.
Oh, I see.
And as I mentioned,
So what is the two morphism connecting trivial one morphism?
the first one, the top.
A plus A
Yeah,
minus?
because on the boundary, the one morphism are all trivial.
Yeah.
But in the box, there may be non-trivial.
Yeah, but on the boundary, do you have a non-trivial one morphism connecting trivial, non-trivial two morphism connecting
Yes.
trivial one morphism? They
Non-trivial.
may form a fusion category, but I just know how they fuse.
Yes. This is actually, you can have, so this decomposition is actually a circle. And the circle can connect to a trivial one morphism, it's just a cat.
Okay,
And that's equivalent to the first. And
So how many two morphism connecting trivial one morphism?
here it's counted up to equivalence. If
Yeah,
we
yeah, after equivalence, how many? Maybe only one, only
up to equivalence, then we just consider they are all equivalent. to
all
the
equivalent.
trivial.
Then they just one,
Yeah,
Okay.
this is defined up to equivalence.
after equivalence, yeah.
And if we just consider the boundary theory.
Yeah.
Then somehow if we just consider boundary theory, then there's no assumption. The
Right.
first is intersect. Then there will be actually infinitely many one morphism, so infinitely many boundary conditions.
Right.
So we are taking some additional.
Yeah, up to isomorphism, if two morphisms can go back and forth by three, if connected by three morphisms, we say they are equivalent
Yes.
isomorphism.
Even after isomorphism, there will be infinitely many.
Oh, you know,
Even after isomorphism.
I see.
So that, in that sense, we have another category, just the surface working inside. And then there will be infinitely many one morphisms. But the two morphism is still vector two.
Okay, yeah, thank you.
So can you tell us your
Right.
thoughts about the four-dimensional Poincare conjecture?
Yes. So when we construct this 3+1 theory, we aim to find an interesting four manifold inverse or smooth four manifold. And there's a very nice result by Reuter saying if the TQFT is semi-simple, it cannot detect the exotic smooth structure. And actually, the result could be even stronger, not just the semi-simple. There are some kind of condition that will just imply this will not work. So this kind of example will not detect the exotic smooth structure. But there are two different approaches. One people consider is taking the non-semi-simple TQFT. That's possible. And the construction in some sense partially works for the non-semi-simple case. In that way, we cannot interpret the relation as a resolution of identity. But there's another way to define the relation. And but mathematically, that is only rigorous in 2+1 theory. And that has been developed for 10 years. For 3+1, I think maybe different groups are working on that. I'm not sure how many groups are working on that, but certainly we are trying to figure out what's going on for the non-semi-simple case with 3+1 theory. That's one hope. But actually, if we look at it carefully, even for non-semi-simple theory in very general sense, it doesn't work. There's another crucial condition, and which I would call non-monoidal condition. And it's very, very delicate. And I just feel when I try to distinguish the blocks of fear as candidates of smooth structure, this non-monoidal condition is somehow more crucial. And then there's a quite subtle problem to me. I couldn't figure out it at this point. Whether the reflection positivity condition always implies a monoidal condition. It's kind of making up the unit to the algebra, which seems true. But until recently when we found that phenomenon, we thought maybe that's not true. Just by the end, there may be something with reflection positivity, but there's no way to make up the unit. That seems possible in higher dimensions. We don't have example or counterexample, but that seems the case. If we have that, then I would say that's also a key to detect the exotic structure, in particular for the blocks of fear. We can see the difference when we rotate that using this non-monoidal structure. But it's really a long way to fill all those rigorous parts. Certainly, that's a very hard problem. And this gives some new insights. And also, it has some very interesting, inspiring questions off of that.
You mentioned this two morphism maybe infinite even after this isomorphism, reduction isomorphism, that's three. And I don't know whether that's a concern because we have infinity, that's like an infinity many simple object, simple homomorphism. And from physics point of view, that can be interpreted as an infinity number of particle type because of one morphism is a string, two morphism is a particle. And so, but the concern is that you have finite condition. Usually if you do state sum construction, things like that, whatever you get is semi-simple. So all the number type or one multiple, they all finite. So here it looks like you get something non-semi-simple, or this it's not quite finite. Yeah.
Here, when we have the reflection positivity, everything is still semi-simple. And if we drop that condition, we also have examples like that.
I see.
Actually, I have to say it more carefully. Even though when we have a reflection positivity, before we take the caution, it's not semi-simple.
Okay.
Just like the complete case, the UQSF like root of unity. Only after we take the caution it becomes
Okay,
semi-simple.
I see. Yeah. What I try to say is that the appearance of infinity number for particle type. I don't know whether that's the signature of gaplessness.
Yeah,
Usually when I have a gap, the boundary, in general believe all the types be finite. And so this may be so maybe this is a gapless boundary. I don't know. Yeah.
yes, exactly. That's the part that we don't have a concrete answer. And
I see.
this my student Fan Lu, we are actually computing certain examples, both for gapless example and for gapless example. And we want to just run this machine to see what we have by the end. Whether we get the different category with multiple particles, it's finite or infinite, and it may not be even a different category. That's the part we say there are actual conditions we need to check.
We should thank Zhengwei Liu for a really brilliant talk, and we look forward to his coming again and telling us more.